As rightly said by Dr. Upadhyay, that this will set the context for the coming sessions. Without any further ado, I'd like to call upon our next panel. Our next session is going to be on building a quantum network. Thank you so much. Thank you once again. So our next session will revolve around building a quantum network. The session aims to provide an overview of the current state-of-the-art technologies and research initiatives in building a quantum network, as well as its potential applications and challenges. And chairing this session is Ms. Suma Varuguhes, Outstanding Scientist and Director General, MED, COS, and CS, DRDO. It's an honor to have her here chairing the session. Let's welcome Ms. Suma Varuguhes. Ladies and gentlemen, let's welcome her on stage. And our other speakers in this session include Dr. Nixon Patel, CEO of QuLabs USA. Welcome, sir. Shri Nilesh M. Desai, Director of Space Applications Center, ISRO. Welcome, sir. Professor Bijoy Krishna from IIT Madras. A warm welcome. Professor Kausik Majumdar from IISc, Bengaluru. And also joining us online in this session will be Mr. Sadik Hafizovic, CEO of Zurich Instruments from Zurich. As we just mentioned, that the session aims to provide an overview of the current state-of-the-art technologies and research initiatives in building a quantum network, as well as its potential applications and challenges. I have the honor now of introducing Mrs. Suma Varuguhes to all of you. She is an outstanding scientist and Director General, MED, COS, CS, DRDO. She is heading 6 major DRDO labs: Center for Artificial Intelligence and Robotics, Scientific Analysis Group, Solid State Physical Laboratory, Joint Cipher Bureau, DRDO Young Scientist Laboratory, and 2 semiconductor societies. During her illustrious career of approximately 34 years, she contributed towards the development of the first indigenous planar near-field measurement facility for the Akash radar system, airborne maritime surveillance radar, and development of the first indigenous airborne active electronically scanned antenna. I hope I got it all right. I request Ms. Varuguhes to kindly begin the session with her special address.
Well, good morning, everybody. As I was introduced here, I should say I'm new to the quantum technology lab here. But looking at what we are talking about, building of quantum networks, we just go forward. I would like to thank the organizers here. And on behalf of DRDO, I thank all of you for giving an opportunity for DRDO to showcase its job. We have seen the revolution that has happened. The 19th century, the machine age, the 20th century, the information age, and the 21st century being the quantum age. That is what it talks about. Ever since Feynman's address of 1982, which proposed the quantum mechanical phenomena to perform the calculations, I think the interest in the quantum computing has gone very high. And today, subsequent to that, we see various algorithms and various computing milestones have been achieved from the framework that was set up by Dr. Feynman to simulating the computer systems on Turing machines, to Grover proposing the reduced complexity quantum search algorithms, to Shor's quantum algorithm for factoring the integers and its prime by substantially reducing the complexity, and the list goes on as we see how the timelines have gone through the complete thing. And from looking from the point of worldwide efforts that has been happening on the quantum technologies, we see almost all part of the world has invested heavily on building up this quantum technologies. And if the what should I say, if the cost goes the way it is, by 2022, there is almost around $30 billion that has been pumped into the quantum technology. So when we look from why the interest in quantum technology has happened, I can say that coming from the DRDO field, I can say that quantum warfare is the quantum jump, I should say, in the military technology, be it inertial navigation systems, the chemical detection systems, the communication systems, the electronic warfare, the radar systems, or the underwater warfare, anything you name, it is moving towards quantum, and that is what has created the interest of pushing and funding the quantum technology development across. And certainly this has led to the quantum race, where we see that Europe has launched almost $1 billion, where the complete quantum communication and infrastructure that needs to be operationalized by 2027. And likewise, China's almost around 11 billion has been spent towards development of computing and communication infrastructure by 2030. And together with Europe, US, UK, almost around $10 billion, which is a race towards the quantum superpowers, which is happening. So why this interest, and what is the significance of quantum communication if we look at it? Today we know information is everything, and the information is the basis on which we move our digitized world, what we have connected today. If we look from that, basically we see that today's world, the sensitive data is typically encrypted and sent across fiber or other channels together with digital keys, needing to decode the information. I don't know, I think it has skipped. It has not gone through that. Yeah, the data and keys are sent as classical bits, either as a stream of electrical or optical pulses representing ones and zeros, and that makes them vulnerable because the smart hackers can read and copy the bits in transit without leaving a trail. I think that changes when we move to the quantum communication, where it takes the advantage of the laws of physics, I mean the quantum physics, to protect the data. The laws allow particles, typically photons of light, for transmitting data along the optical lines to take on the state of superposition. And the beauty is, from the cyber perspective, that if any hacker tries to observe them in transit, their fragile quantum state collapses to ones and zero. This means that hacker cannot tamper with the qubits without leaving a telltale sign. So the typical scenarios, what we see is usage scenarios, especially in the military warfare, is the tactical key distribution for encryption during the conflicts or wars, key sharing between the ground stations and the satellites for encryption, and key sharing between the satellites for encryption and mutual authentication. So if we look from that point, we see that there is a key generation to key registration to key storage, key distribution, usage, rotation, backup, and recovery, and revocation and suspension to the key destruction. This is the typical cycle of the key distribution that is happening, which can happen either over a satellite-based communication or ground-based communications. So when we move towards the quantum key distribution system, there are some basic working assumptions that we need to consider. Any attempt at snooping of the photon streams would introduce errors due to the non-clonability. That is the first assumption we are making, which is true to a large extent. Errors are estimated from the correlation of states of photons reaching the detector with those at the time of leaving the source. Errors could be due to snooping attempts or channel noise or both, and it is treated as snooping in the quantum key distribution systems. Quantum bit error rates or surveying decoy rates are used to decide on accepting or discarding the key. So the concept of privacy amplification based on Kuber estimates is sufficient to cover for the leakage of the key information due to snooping. So this ensures a more secure communication. When we look from that point, we see what are the components that are required for a quantum network. We have a source, which can be a single photon source, a detector, single photon detectors, quantum memories, and also quantum interfaces, and the repeaters. These parameters directly impact the performance of quantum communication system. When we look from the quantum networks per se, photonic qubits are the preferred choice due to their resilience. The network for quantum communication, the case is similar to the classical parallel computation. Qubits need to be transported over the short distances. Custom quantum channels are required. Optical switches, which preserves the coherence, has to be designed, and quantum teleportation could be an option too. Network for communication, mainly the main application is the key distribution as brought out. For key sharing for secure communications, qubits need to be transported over larger distances, which can be greater than thousands of kilometers, and existing telecom fiber infrastructure to be used as an option. When we look at each of these components, we see that sources, when we talk about the coherent weak pulses or the entangled pair photons are used as the sources. This entangled pair of photons created from a stream of photons passing through nonlinear crystals. That process is called spontaneous parametric down conversion, which is the need of the hour where the country has to develop it. Of each pair, one photon travels to the sender and other is kept by the receiver, and the entangled pair creates the true random key string at the time of measurements at the end point. The next aspect of the network being the detectors, the avalanche photo detector diodes, which are inexpensive, but however, we know the efficiency of this is very low, almost around 10%. So the need for superconducting nanowire single photon detectors are the latest options, which claims to have efficiency of more than around 90%. And we have to reduce the stray photons and dark counts, which has to be minimized over this. The next aspect is the networks for quantum communication. Technologies for quantum communication, which can be over the fiber. The range is, however, limited to 100 to 150 kilometers. Options to extend the fiber, the range over the fiber, either we have to go for a dark fiber, which is both costly and limited option, And trusted repeaters, either using satellites or memories, has to be looked into, and quantum repeaters, which requires the quantum memory, or free space transport is another option where the line of sight over the limited range and also via satellites for longer range or inter-satellite secure communications are the way forward. Coming to quantum memories, we see that the concept, which is to transfer or absorb and release later, this into the solids, which is an ion-doped NV centers or atmospheric gases, which of rubidium nature. The performance criteria of these memories are stringent in terms of their efficiency, the storage time, which can stretch up to millisecond to second, and coherence and alignment is important to have the fidelity, and speed of operation or the bandwidth is also a requirement, which I know is in a very exploratory stage, and probably we will be hearing something down the today's session on the quantum memories. And similarly, when we talk about the quantum repeaters, like which uses the entangled photon pairs and the Bell states, and need for quantum memory for short-term storage and receiving end becomes an important thing, or we have to go through the teleportation process where the outcome would be one of the 4 Bell states. This could be communicated between Alice and Bob. This is also in a highly, I should say, explorative stage. The next aspect of that would be protocols on which we will be communicating. This is, though originally proposed as BB84, as all we know, which uses of a source of single photons that can be polarized to represent the zeros and ones, mostly uses photons of 1553 nanometer wavelengths, and now various variants have been proposed for both fiber and free space QKD applications. And coming to the entanglement-based method, originally proposed in 1991 as E91 protocol, now a number of variants have been proposed both on fiber and free space QKD, and the advantage of this being it does not require a true random number and hence becomes a source independent system. The next aspect of the architecture would be on the electronics, which looks for the field programmable gate arrays as the computing core, time stamping and synchronization of devices to the accuracy of picoseconds is the requirement, and the key establishment software, which calls for time synchronization between the source and the detector devices, time correlation between the detected photons and their release from the source and the raw key extraction, calculation of QBER, visibility and assessment of leakage, and also the privacy amplification for neutralizing leakage uses a reduced hash function. When we look at all these things, I have got a chit, I have to finish in a minute. We have the challenges ahead in terms of compatible coexistence, the entangled photon procedures which are inherently probabilistic, leading to photon losses, and to scale up the network it has its own set of challenges, and quantum frequency conversion modules has to be used. The next is, as I brought out, timing is everything. Synchronization is the crucial part. Timing requirements for emitted photons are strict. The time difference between NV centers needs to be less than 1 nanoseconds, and many technical solutions are needed to bring a large-scale quantum network, that is, to make quantum internet closer to reality, addressing both the synchronization and compatibility issues. Also, we have to bridge the distance. I will just, using probably the quantum repeaters, I just skip this. And coming to the enablers, when we talk about production and employment of high performance quantum technologies, these are some enabling factors that needs to be there in place. in terms of foundries for synthesizing quantum systems from source materials. We need high performance electronics, optic and mechanical thermal systems for control and isolation systems, nano and micro fabrication facilities for manufacture of devices that integrate and control the systems with quantum systems, high performance software stacks, benchmarking and testing of our simulation facilities to accelerate, develop and support the user adoption, and finally the quantum ready workforce. And we see that this is the famous thing which we know that China has achieved this both in terms of fiber and also in terms of satellite application. Coming to DRDO's efforts in this direction, DRDO has developed the quantum random number generator. I think it is being exploited by some of the army units today, where the TOT has been given to the industry. And DRDO, along with IIT Delhi, has designed the fiber-based QKD, which showed the performance over two cities, that is Prayagraj and Vindhyachal, almost around 100 kilometers apart. When we look at the quantum communication, this would be the future of our communication, where everything is in a connected world and we need to secure the systems. And this is where I think all of us have to work together. And I think with this, I'll skip this and say thank you. Thank you.
Thank you so much, Dr. Varuguhes. And well, due to limited time, I would request our eminent panel to kindly be brief. Introducing Dr. Nixon Patel next. He is a technology innovator and high integrity leader, having more than 30 years of experience. He is the CEO of QuLabs, a mission-driven research lab to provide the world and India its first quantum internet to deliver reliable, high-quality, cost-effective, efficient, scalable, and secure quantum communication solutions with quantum internet platform and software stack. Dr. Nixon Patel, please.
Which goes up? Yeah. Okay, sorry. Yeah, good afternoon, everyone, and sorry to keep you between the stocks and the lunch. I know it's pretty hard. And thanks everyone, including our organizations and the delegates to our talk here. So basically, as you see, our efforts are in putting something together for the quantum internet for India, and especially with the special focus on quantum memory. I'll just walk you through because of lack of time. Yeah, so we have been at it for about last 5 years. We have been the first to set up a quantum optics lab in India. We are also one of the first quantum fintech company to be authorized in the gift city that Prime Minister Modi has established in Gandhinagar. We have 12 plus IPs in the space, and we are we are in the process of setting up a quantum network communication center with IIT Hyderabad, and we just signed the MOU a couple of weeks back. And there we are also going to be setting up a quantum certification, 4 cores. Also, recently we signed a MOU with CQN, which is an equivalent in US that is creating the quantum internet, and it's being supported by NSF with about $50 million. So there are 2 special things that they want to work with us in terms of our quantum network simulator and our quantum memory. Then we have, like, I think one of a very large pool of quantum scientists full-time, or 30 plus. It's very few companies in the world, handful have that. And we are generating revenue through quantum networks in the last few years. So there are a lot of firsts. We are like one of the top 6 in quantum AI, considered one of the top in quantum startup, and we are put in the same league as Google and the likes. So basically, I think what quantum communication brings, what classical couldn't, is like obviously everybody knows, and I don't want to go into too much detail, but the classical communication has amplification possibilities because it can copy the qubits and quantum cannot, and that's where our focus is in terms of trying to make that through repeaters and quantum memory, right? So besides that, we have about 30 quantum secure direct communication protocols. We have 6 patents, which are part of our stack for our quantum network simulator. And as all of us know, that QKD is mostly for point to point, and if you want to extend, it's very difficult. So obviously, QSDC, and in QSDC, some of our protocols don't even need entanglement. So this is a very large effort has gone in the last few years to build up the entire stack. So looking at these steps of development, like you see here, and because of lack of time, there are this whole QKD problem with the trusted repeaters network requirement, and then you have, as Dr. Varuguhes said, prepare and measure networks, and we are building on top of that in terms of through that into quantum memory, and obviously there are 3 different generations which we'll go through in the coming slides. And if you see some of these other players, as I said, we have partnered with the Tucson Testbed Center for Quantum Communication USA in Boston, and also there's a lot of effort by China, and there are some effort in Europe, and we are trying to do similar things for India. This is our quantum network architecture. I think it's very loaded slide, and I don't want to take too much time, but for those who want to understand, equivalent to the 7-layer OSI, we have a 5-layer QOSI, quantum open systems interfaces. And if you see, there's a physical layer, link layer, network layers, so forth. And what it provides is, if you look at this part of the picture, and if you see those 3 dotted lines, and that's the creating end-to-end entanglement, and there is a whole process of entanglement generation, purification, swapping, purification, so distillation. And on top of that, if you see in the application layer, that's where our quantum secure direct communication protocols and QSS stand. So, okay, coming to the core of the discussion, right? So, as we said, because there's a no clone, you cannot beyond certain distance because of decoherence. How do you extend your quantum communication channel, right? That's quantum internet or whatever. So you typically go through this whole entanglement creation, then you do various level. We are still doing a generation 1 level of a repeater. That's what we are building, which kind of does just basic purification. And I think the next generation where you'll need more of non-heralding error corrections, and again, error corrections at the link layer and error correction at the end-to-end layer, right? And error correction at the end-to-end layer would come in layer 3. So here, if you look at this various breakup, right? So what you do is quantum network utilizes photons to transmit, store, and exchange information, right? So here you have Alice and Bob, and then you have some entanglement sources here, and then once they need to be, you do some kind of Bell state measurement. Bell state analyzers will kind of annihilate these 2 photons, and you'll have a connection between Alice and Bob. So what are these 3 generations, right? The first generation is where you have, if you look at the errors, the loss of error is a big challenge, right? We talked about that. So there's heralded entanglement generation, and then there's a heralded entanglement purification, and then the other 2 rows are quantum error correction and quantum error correction, the operational, and then loss layer. So if you see in the columns, the tick marks tell you what we do at generation 1, what we do at generation 2, and all of us there's not a quantum repeater in the world that does anything beyond 1G. 1G also, that too, we don't have any commercially available product, right? So it's early stages, I think there's only one other company in the world, Connect, or whatever it is, in US, which has a tabletop version of a quantum memory, unlike like we have, based out of 87-based rubidium vapor cell. And theirs is based out of something called EIT, electromagnetic induced transparency. We have some other approach. We'll cover some of that. So what are the challenges in the repeater, right? There's a memory efficiency and a storage challenge, right? So I don't want to get this too much detail, too much technical stuff, but if you look at the vertical axis, there's the secret key rate, and you look at the distance, pretty soon you see 10 to the power 0, and there's a cross there between no memory and then through something called EXE is excellent, and EN's in enhance, and EN's enhance efficiency. So if you look at the columns in terms of different efficiencies are defined there, and what coherence times you get, that's the amount of time the quantum state can be preserved, and then how much repetition is required. So you'll see the throughput change, right? So, and what we get from our simulation and modeling is the E, the lower part, which is pretty good. So other challenges are the frequency conversion, right? As we know that it has to operate at telco frequency, and from moving from the regular 780 or 785 to telco frequency, the whole conversion brings in various inefficiencies, right? So there are different techniques, the four-way mixing, which we are trying to implement, and that has certain advantages because you have two pumps and one input signal and the output signal, and then you play with that to optimize. And part of that, we need also clock synchronization. So we are building our own atomic clock, but definitely we will take help from Professor Umakant. This is some more in terms of challenges in the repeater and the quantum memory creation in terms of the creating the source and detection. And as again, Professor Varuguhes, Dr. Varuguhes mentioned, it's a very challenging thing, right? So our goal is by next 18 to 24 months to try to have all these single photon source or entangled photon source or some of these various components to be indigenized and create in our lab. So where we have a lab in Hyderabad where 30 plus scientists are working. Because it's been a very bad experience. It took us almost a year to set up the lab despite spending a couple of $1 million to get components from Germany, France, or US. And there's like, because of supply chain and other kind of limitation, if these kind of things have to happen in reality in India, I think all these components have to be indigenized in the next 3 to 5 years. Otherwise, I mean, yeah, you know. So these are some of the data transmission results that we have obtained, the SPAD results we have obtained, and I don't think we have time to go into too much detail, but it talks about the photon detection efficiency. So this is a good chart which kind of gives an overview of different types of quantum memories, right? We are working on the EIT warm vapor one. So you see the highest efficiency is only 17%. Our next goal is to do the cold atom. And again, there are some professors, some labs. So we have 5 or 6 labs in various IIT, Roorkee, Hyderabad, IIT. We have some relations with ISI and so forth. So where I know that also in IIT Roorkee, I was there yesterday, they're putting up something on cold atom which even IISr Pune has. So I think that's our next step to see how we can increase the efficiency. And if you see the storage time also goes from 1.5 microseconds to 325 microseconds, right? So that is our focus, and part of it will be also in the GEM, the gradient version, echo memories. That also, if you see, is pretty high efficiencies. But again, if you see the storage is kind of medium. So there are different techniques we are trying. And our goal is that by end of this year to have by June we'll have a tabletop version done, and by end of the year we should have a compact version of a quantum memory that can be delivered. And then another 12 months will be, by end of 24 we should have a chip version. So that's our goal. So there are these different advantages for quantum memory for what we are doing in rubidium, because it can be done at room temperature. We can create a compact size and cost effectiveness. So our goal is to currently only one quantum memory was created by this Connect, which US government has purchased for about $100,000. And from what our numbers are, our calculations are, we'll be able to do it sub 40K kind of a price point. So these are some more challenges, you know, environmental challenge in low storage in the quantum memories, right? Then these are a different technique, AFC-based technique, and there's some improvements that we are seeing in our experimental results. So, I mean, it's again too much technical to deep dive. But yeah, that's where we're talking about the four-way mixing, right? So that kind of helps suppress some of these errors. So this is another technique that we are currently embarking on, the magneto-optical MOT, we call it MOT in the memory. And I'm sure the early results are showing much better storage and much better in terms of coherence. So I think that is the next thing that we are putting together in a cold atom version. There is, again, I'll kind of skip this because it's AFC. This is the GEM, gradient echo memory, so I think too much detail. So what's our approach? As I said, first stage is to, obviously it's a rubidium-based approach, 87 vapor-based approach. This is the kind of fidelity and storage time and efficiency. The current efficiency that the other company in the world that has, only other company has 5% efficiency. I think we'll get to 10 with our current approach, and with MOT, I think we will end up getting much more. So problems to tackle, these are some of the problems which are very obvious, you can read to that. And the stage 2 is the MOT-based approach, which I think will reduce certain, with trapping atoms using laser cooling and some other techniques, reduce susceptibility to the noise, and so that way we'll get much better efficiency. It looks like our modeling and our simulations are predicting like 69%. So just as an aside, we have world's first blind quantum simulator. We also have create our own quantum network simulator, which is, I think, attracted the CQN, the US counterpart making the quantum internet, to partner with us because they think we are much advanced stage in terms of what we have. So that kind of helps us design some of these protocols. And this is our lab that we did in Roorkee, IIT Roorkee lab, right? So these are some of the numbers you see, what it is. It's 780 complemented by various optical components. Transparency window was 6.66 megahertz. So these are some technical terms, but, and these are some of the results. People who want to check it out, we can talk offline with the optical switch AOM and RF drivers and some of the spot size and EIT peaks. This is the stuff I think most of you will relate. Most of the other stuff, many of you, except some professors sitting in this audience, may not relate. But so obviously we need quantum memory, right? Everybody understands that. Because you want to extend beyond 80, 100 kilometers, any communication that needs a repeater, and repeater has various components, and that, I think, quantum memory is the key thing. And why it's important? Because there are not many players in the space from our perspective, right? So it's a green field, and I think it's going to enhance the various things that we can do. It's first time happening in India. So all our R&D, almost 99% happens in India, though we are a US-based company, and partnered with CQN, and we got just another email this morning that there's a Toronto-based, there's a lab called CDL. They kind of accepted us as a partner. And also we're working with certain other players in Switzerland and Netherlands, which will be useful for us to do the chip-based, because India does not have still these fabs, right? So that's some of the global players we are working with. And so I guess that's so I want to leave it short so that anybody has any question. Thank you.
So as I mentioned earlier, we'll be taking up the questions online and replying to them later on. Our next keynote address is going to be by Shri Nilesh M. Desai, distinguished scientist. He's currently the Director of Space Application Center, ISRO, Ahmedabad. In his about 37 years of dedicated and illustrious engineering and research career at ISRO, he has been involved in design and development of various projects at ISRO. He has represented ISRO and India at various international forums, and he is the recipient of ISRO Performance Excellence Award, ISRO Individual Merit Award, and ISRO Team Award, just to name a few. Shri Nilesh M. Desai, please.
Good afternoon. With so many experts and stakeholders here, I am like a novice in these audiences. But anyway, I'll try to do justice to the task given to me, quantum technologies in satellite communication. Yesterday we had a very beautiful launch of 36 OneWeb satellites. And the day is not far when we have similar swarm of quantum satellites. That's what I will bring out some of these aspects related to that. Communication generally, as George Bernard Shaw said, that single biggest problem is the illusion that it has taken place. And here with quantum, we try to create that illusion so that hacker doesn't be able to know about our communication. All of you know Honorable Prime Minister's Science, Technology and Innovation Advisory Council, where quantum frontiers has been identified as one of the major area, and that's why we started these initiatives in ISRO, in Space Application Center, almost 5 years back, and I just try to bring to you some of the goals we have achieved. And as all of you know, ISRO is more, we do R&D also, but we are more action-oriented organization. So how we have done the action, I just try to bring about those aspects. All of you know, last year's Physics Nobel Prize was awarded to these three gentlemen who worked on quantum physics. And that itself is an impetus to all of us to pursue these studies further, R&D and whatever other technology development related to that. And as the morning we saw that 2025 could be the International Year of Quantum Science and Technology. So all these pointers to the great future which quantum communication is going to have. All of you know we have a normal classical channel of communication which we are all familiar with, whether it is a terrestrial network or fiber optics or RF communication through satellites. So this has been there, and we are now adding what we call a quantum channel where data rates are not important. That is the major aspect of that. For some of whom we are uninitiated, that what we know is that when we transmit our password or the key, that needs to be protected. And normal communication will happen, the encrypted data can go through the normal classical channels. So we want to take care of that key through this quantum channel. And applications all of you are well aware of in various finance, banking, government, defense. All of us know about the importance of keeping secrecy. And of course, in our all various commercial dealings, our OTP protection, that is the major thing which now all of us, with a lot of cyber frauds happening. And with the India going for its own GPS system, that is NAVIC, transmitting that restricted services, especially for our strategic sector, how to transmit that restricted key. So that is also going to be a very important element. This is how we are conceiving, finally, after doing all the research and development on ground in the labs and taking help of academia as well as other research institutes, as well as industry. Finally, we want to build a network, and this network will not be only satellite based. It has to be obviously hybrid network, because satellite, although satellite has an infinite reach, all of you know that it can reach anywhere in the world. But as far as this technology is concerned, we need a hybrid network, because you can't set up earth stations everywhere, all across the globe. So it has to be a combination of earth station along with the hybrid terrestrial network. And usage of memories and repeaters and all is going to be there in a big way. So China and Japan has already demonstrated, Singapore has also demonstrated in some way a quantum experiment. We are also going to do very soon. I'll come to that aspect also. But this is how we are trying to conceive a network for India, an India-centric network. We are aware of the developments having taken place all across the world since last almost 20 years, 2005 onwards. Many countries have flown various experiments across various satellites, so that is happening. Many have announced, but they were not realized, although they are still working on that. So on the top, we are seeing some of the experiments which have been already conducted by Japan, China, Singapore, all these people, USA, Europe. But there are many of them which have been announced, the people are working on that, but they are still not over. Misses is one of them, which was very famous and well publicized by China. Similarly, we had Socrates from Japan, and Singapore had a Spooky, which is like a loopback system on board itself, and the results were verified on ground. So these are some of the experiments conducted on board in satellite, and hopefully India is soon going to join in that. As far as technologies are concerned, it is basically related to what we do is remote sensing, communication, navigation, and its associated applications. All of us are well aware of that. And in that we'll be adding quantum communication and quantum sensing or quantum radar. So these are the two new technologies which will feed into the work ISRO has been doing as far as communication, navigation, and remote sensing is concerned. And the technologies involved, like a classical communication channel, starting with a transmitter and a receiver, which are the two essential elements, and to take care of the medium, so whether atmospheric modeling, because quantum, all of you know, it is through photons, so how photon absorption takes place, how photon behave in an atmosphere, so all those studies, which locations are more suitable for setting up Earth station, so all these things are part of the technology development. And of course, other aspect, when you want to put a quantum communication system in a satellite, then orienting it towards Earth station, so PAT mechanism, pointing, acquisition, and tracking. So all these things become very critical and important. And of course, the sources and the detectors, which many of you talked about that. So these are also going to be the technologies which will be needed to develop that. So as far as overall technology of a system are concerned, baseline technologies, as I said, transmitter, receiver, time tagging and synchronization, about which Madam also talked about. So we are planning, right now GPS is being used, but our aim is to use our own navigation with Indian constellation system to achieve that nanosecond sort of timing synchronization among various network elements. Then protocols, whether it is for single photon or entangled photon, whether BB84 or BBM92, which are standard protocols. So developing new protocols, that is also part of the exercise. And as I said, we need a pointing, acquisition, and tracking system on board and on ground also, so that you get align the Earth station with the satellite. So that will need, again, a telescope with PAT system and channel modeling to take care of the ideal locations where you can set up Earth station. And of course, source, when you go for radars, especially for strategic application where stealth target also can be detected. That is the use of these quantum radars. So you need a microwave quantum source, which is going to be one order difficult than what we are achieving right now with an optical quantum source. So these are all the technologies which we are working on. Many of you are also working on in academia, in other research institutes. And as far as system level technologies, whether it is single photon based or entangled photon based, whether QKD is over a moving platform, you try it out on a drone or aircraft, and then go to satellite. And to take care of that, we are planning two of these payloads, as has been mentioned here. Quantum entangled source in space that studies, as well as one technology development satellite, which will go from LEO to GEO. So you get information not only from LEO orbit, and also from GEO orbit, you try to test out this quantum communication. So these are the two experiments which ISRO has planned out. And of course, it will need an optical ground station to aid in communication like a normal other Earth station. And then we'll have our own dedicated opto-quantum communication program consisting of, as I said, multiple satellites. So I will one by one just briefly tell you about that. So this is all have been already achieved. This is ongoing right now. Pontis payload is under development at SAC with the help of our PRL team also. Dr. Singh is here. And we'll have another payload on board our technology development satellite. And then we have various technology development programs. And the final result will be a quantum communication satellite program of the country. It will not be restricted to ISRO. It belongs to the whole country, and that associated battery of network of optical ground station. So and some of the associated technology development related to that, whether it is photonics or various ASIC development. So now I'll just show you some of the experiments we carried out. We started working in 2018 onwards, and with the support and help from PRL team here, we have carried out these experiments. So first one was the single photon based quantum key distribution across space, that is from one building to another in space. Because normally in lab everybody can do 30 centimeter, 50 centimeter, or between two tables and all. Many academia, everybody is doing. So we have carried out this experiment from one building to another in our Space Application Center campus at Ahmedabad, spaced almost 300 meters apart. And we transmitted a key from one place to another, transmitted data also, transmitted text messages, images, and videos, and carried out a video conferencing also. So normal data will flow through our classical fiber optic network, and the quantum key went through the space 300 meters apart. It was used to decode the data sent from one place to another, and that's why how we carried out, and it was very well reported in media also, as all of you are well aware of. So these were the unique features of this particular experiment which we carried out in March 2021. And after that, with the help of our PRL science team, so this was what it was reported everywhere. We carried out in November that year another experiment with an entangled photon source. As all of you know, entanglement provides you one order of secrecy or security better than a single photon source. So that experiment was carried out with an entangled photon source developed by our PRL science team. And then there we achieve around 300 kilobits of data transmission in space. And similarly here we achieve around 25 to 30 kilobits per second. So this was how the other experiment was carried out. Again, everything was same, Alice, Bob, everything, 300 meters apart. But the only difference was that instead of single photon source, we have used an entangled photon source. And then you have the associated PAT and other mechanism. So this was the other experiment we carried out. This was also very successful. And these are the results. So as I said, with single photon, you achieve higher data rate. So this will be the candidate for satellite communication. This has still a long way to go, because right now we are able to achieve only 2 kilobits per second in even a 300 meter distance. You can imagine now when I am at 500 kilometer altitude from space and lot atmospheric, all absorption and other things will come into picture, what will be the result? So we have still a long way to go. It is a very important research area, but right now we are going ahead with the single photon source in space when it goes in the operational phase. As an experimental phase, we will be doing both the experiments. So this is how we, as I said, we decrypted text, then images, ISRO headquarters pictures, picture of a person, logo, everything. And then we carried out a video conference also. And this is how the payload is under development at SAC Ahmedabad, and it is going to be launched in the satellite which is already on the launch pad, PSLV C-55, which is going to be the next launch of ISRO. There we are, with the help of our PRL team again, together we are building this Pontis payload, where entangled photon source is used in a look-back manner. So the way experiment was carried out by Japan, China, and Singapore, we are trying to repeat that, and soon, hopefully, India will also be joining that club of countries who have demonstrated quantum entanglement as well as quantum communication in a look-back manner from space. So we'll get the telemetry signal, and from that we try to demonstrate that it is working in a look-back fashion. And then that will be followed by, these are the hardware which has been built. So there is an electro-optics module and there is an electronics package. The total weight is around 15 kg, and we'll consume around 134 watt of power. So this electronics and optics is going in space in our next PSLV flight on 22 April, and hopefully we'll achieve these results which we have planned out. So it will be a good achievement for the country. And similarly, we have planned out another communication payload, a quantum communication payload in a geo satellite. So this satellite will be launched in LEO, and then it will move through a EPS system to the geo orbit. So we'll get time to do experimentation for almost 3 to 6 months when the satellite moves from LEO orbit to geo orbit. So that will give us another dimension of the experiment which we carry out, and here we'll be having a single photon source. So these are the developments. So this is the conceptual structure of this particular payload and the development which are going on at SAC. And some of the other development related to photonics development, whether it is a single photon source or entangled photon source, and the associated detectors, avalanche photodiode, which Madam talked about, or SN-SCD, that technology. So both the developments, we have started working on that, and with the help of academia, people like Dr. Das and his team. So we are hopeful that we will have our indigenous solution to all these things. And the final will be like an optical transceiver. We should have everything within a chip. So that will be the ultimate when we want to realize such quantum network. So these are the technologies which have already we started working on that, and it will work, it will serve the purpose of not only quantum communication but quantum radar also. Only difference is, as I mentioned, the photonic source which has to now work in a microwave domain. So that development is going to be, as I said, one order difficult compared to what we are doing right now. So this is the timeline. We started working in 2018, and by 2025 we are hopeful that the country will have a hybrid quantum network where we will be able to securely transmit these passwords or keys all across the country without any problems. And this is the proposal which now at ISRO level we are working on, a combination of 2 LEO satellites and 1 GEO satellite. So that will go as a final operational way. Right now what we are testing is just payloads across these 2 LEO and GEO satellites. But this will be some sort of experimentally or quasi-operational system which will demonstrate all sorts of communication between LEO to GEO, GEO to ground, LEO to ground, and between LEO to LEO and LEO to GEO. So all type of communication with optical and quantum channel will be demonstrated with the combination of these 3 satellite systems. So this will be the payload which will be there on all the 3 satellites, and that is going to be the work which we'll be doing next 5 years. Another important element, as I was mentioning, was that we have to set up optical ground stations. Now optical ground station you cannot set up anywhere. I cannot set up in Delhi, because Delhi has its own other problem. Already pollution, all these things, it affects communication. So right now these 4 candidates are there: Mount Abu, Ponmudi in south, Space Application Center Ahmedabad, we have set up experimental ground station, and Hanle Ladakh, that is the most ideal site because the ambient noise has to be minimal. And some of the frequencies which we use, laser communication, 800 nanometers or 1550 nanometers, these are the 2 major candidates. So each will have its own requirements as far as setting up a Earth station is concerned. So this is the, on Earth station or ground station also you have elaborate setup which you have in a satellite. And these are some of the setup with this, the left hand side what we are seeing is the setup which we already have in Ahmedabad. A 700 millimeter telescope is there. Finally we'll need around 1 to 1.5 meter type of telescope in that Earth station, and as I said, Hanle will be the most ideal location for setting up the system. But that's why we need a hybrid network, because we cannot have Earth station. So we did some atmospheric channel study also, and from that you can find out that Hanle and Mount Abu. These two are the most ideal sites, even out of these four also. So, like this, so many such studies are also needed when you want to set up a quantum communication setup in the country. And this is going to be how the communication will take place, whether it is single photon source or entangled photon source. And finally, this will be the hybrid network which will cover the whole country. So it is a combination of satellite system as well as a battery of repeaters and memories, what Mr. Patel was talking about. So that will be the ultimate. Hopefully within next 20-25 years, country will build this particular network as far as communication. Thank you.
In the learned panel, we also have Professor Bijoy Krishna from IIT Madras. He's one of the core founding faculty members of the Center for NEMS and Nanophotonics, CNNP, sponsored by Ministry of Electronics, Information and Technology. His present research focus is on silicon photonics devices and circuits, optical interconnect, and quantum optic application. Professor Bijoy Krishna, please.
Good afternoon. Thank you very much for inviting and giving opportunity to talk about. And thank you for the previous speakers setting the stage. The ultimate objective required for quantum communication or quantum computation is integrated photonics. And I am leading Center for Programmable Photonic Integrated Circuits and Systems. And you know, microwave and quantum both are, I think, many times coming, starting from the minister's talk in the beginning. So half of our heart in microwave photonics and half of our heart in quantum photonics. Basic technology same, silicon photonics, CMOS technology. So I'll be talking mostly what are the efforts we have initiated at IIT Madras for quantum photonics. So bit of background, I will be talking scopes and objective and team infrastructure and silicon photonics, the quantum technology things. Yeah, so this is something we have, I myself has already 25 years of experience in integrated photonics technology, and IIT Madras we started in 2006, about 15-16 years of silicon photonics technology developed. And now we have this Center of Excellence funded by MIT. And our objective is that pushing silicon photonics technology in the direction of quantum photonics as well as in the microwave photonics. And the research objective is the PACE, of course, product research development and manufacturing model. As I mentioned, got to go back. How to go back? This one. Yeah, sorry. So our goal objective is the product based. We just select the product and find out the specification. Based on that, we work out. And so it includes the design, chip design, fabrication and system in package, and for that we are also collaborating with our industry partners, and we have in-house process facility, of course, and basic level circuit demonstration, everything testing we have in our labs. And when we go for complex design, complex circuitry, we have collaborator, we have also signed with foundry, silicon photonics foundry like Silter, Malaysia. We are working also with them to develop, and also we have the industry partner Desai to Microsystem, where we are actually making something like box where you need to use that in the field. So these are the facility. I can skip. I think I just can mention that we have the 4-inch process facility, 4-inch silicon wafer process facility, entirely start to end silicon photonics process for passive and active reconfigurable photonics. And we do have all the characterization facilities, and we are developing for fully wafer scale process, because ultimately you need scalable technology where you get to manufacture the chip, package it, and so on. So you need a robust testing facility. So that those things also we have at IIT Madras. Yeah, this is the team, and we have faculty colleagues. They are actually working in 6 different verticals, just starting from what I mentioned, that design to simulation and fabrication and process, and of course packaging. A dedicated CTO is there. And to demonstrate, to ultimately, when I mentioned that we have to work for product research, development, and manufacturing model, so we are closely working with industry leaders, and we have the board chair, industry advisory board chair, and along with that, starting from Broadcom to Broadcom and Intel, and also Global Foundries, and some startup also, except photonics, all of them are some way 5G or photonics related work doing, quantum photonics related work, and they are guiding us, supporting us. Yes, so now if I just, as I mentioned that we are for integrated photonics purpose, I need some kind of background to set the stage. So if you see quantum photonics, the applications, many speakers already mentioned that the application is all around, starting from quantum metrology, quantum key distribution, communication, imaging, simulation, computation, so on. So what are the fundamental requirements for all these applications? Either you need a single photon states, superposition states, and then entanglement states. So whenever you are talking about integrated photonics, you have to keep all these in mind. Okay? So basic optical components required. So these are the function of qubit, so the quantum level things, and many basic optical components, they are not really quantum, they are classical. So you need to manipulate all these quantum bit photons. For that you need all the classical components. So some of the, of course, photon detector is a quantum. So those are the devices already known for a long time, and people are using for many application demonstration. For example, to talk about the quantum experiment, I can take reference of this picture. So here, so slow it something. I don't know where is the sensor, it is taking slow. Yeah, so this is one experimental setup demonstrated in 2013, University of Bristol, quantum teleportation. So this is the room size experimental setup. To establish this setup, they took 3 months. What sort of stability, what sort of accuracy required, that says all. I think some of our colleagues like Urvashi, RP, and Chandru, they have started, they are working in quantum photonics. I can understand their pain. Okay, so this is the requirement. So all these components you need to align, all those type of things, and then only you can get successful experimental results. So for that, it would be great, as everyone's talking about, for future ultimate goal, objective is the quantum photonic integrated circuit, something like this, where you can get compactness, stability, flexibility, and of course scalability, cost effective, and programmable. So silicon photonics is ideal platform because you have the established foundry, commercial foundry available, and you can co-integrate electronics and photonics on chip. Directly you can fabricate using same sort of technology process, and you can have like a photon guiding, wave guiding, everything by means of highly confined optical waveguide core in the dimension, submicron dimension, sharp bends, compactness you can achieve. And of course you can get photon pair generation, not SPDC, which is not available in silicon. However, we have the Chi3 process in silicon. Using that thing, you can get photon pair generation. You can energy entangled photon pair as well as heralded single photon source. Pure photons, you can improve the purity, etc., up to more than 99%, etc. Those type of things you can have in silicon platform. So, if you talk about the integrated photonics, so you need a source side, qubit or photon, and then you need a interference circuit, couplers, etc., and then ultimately you need detector side, single photon detector side, and then electronics. So most of the time, it is already matured. The already classical optics in silicon photonics matured. Commercially, they are being used for a long time, last 1 decade. A lot of products are available using those classical optics. So those are mature. However, the photon size, single photon generation, pair generation, that is somewhat bit challenging. So this circuit we have taken up. We have started working on in our lab so that we can generate a very good, efficient photon source, noise-free, and they can be filtered for application, whether it can be your quantum key distribution or can be quantum computation. So one of the source we consider like a ring resonator where you can actually give some little bit of high power in the milliwatt level, and then because of the ring resonance, electric field will be enhanced, and entangled photon pair like two daughter photon like signal and idler will be generated. However, the generation rate, as I mentioned, Chi3 process relatively low. You have to eliminate your pump down to almost 100 dB attenuation required. So you need on-chip attenuator for filtering your unused pump so that you get certain kind of photon, so that detectable or usable photon counts you can get, so that it is not buried under pump. So after that, you can, if you need, you can just separate them because they are energy entangled. You can use a demultiplexer, you can separate them, and you can herald them also. Okay, so in that way you can use, and certain property we have already optimized using our all the experimental and all the long time experience in integrated photonics. What are the requirements? If you see the right side, generation rate depends on certain parameters, and brightness depends on certain parameters. All those things optimized. So for our results, we are seeing that in this classical domain, we can reach up to gigahertz level generation rate, and also purity you can get up to 99% and so on. Yeah, so after that, just some results. Recently we got some patent. We have filed patent. It is not yet approved. So, what I was talking about, that you need a pump source. Through Chi3 process, you need to generate entangled photon pair, and you have to eliminate on chip. So far, people are using across the globe off chip. So they generate in a chip or in a bulk, and they off chip component they use, they eliminate the pump, and they filter the photons, and they use either in fiber or some other chip. But on chip, if we use source on chip, then what happens? You have to launch the pump, and the pump, whenever you are launching, you need some kind of amplifications. So in the amplification means you are adding certain kind of noise also. That noise also will add quantum noise on chip. So we have a device design, something like this, where you can actually filter your pump, barring all the white noise on chip, and you can get very clean pump source, which can be useful for your Chi3 process or photon pair generation. And once it is done, then remaining part, once it is generated, remaining part also on chip we have demonstrated up to 70 dB. But as I mentioned, we need to improve that up to 100 dB. Hopefully we will be getting soon. Yeah, so apart from that, as I mentioned, if you go for really a circuit, complicated circuit, complex circuit design, for example, you need both Alice and Bob together on chip. They should work simultaneously, and if it is a quantum processor also, you need your source, you need your all the reconfigurable programmable components, and you need a detection, electronics, everything needed together. For that, we are not equipped. In our academic lab, we cannot do that. That's why we are taking help of commercial foundries. For example, here, first chip we have designed, and this is for photon pair generation filter disk. Whatever we have demonstrated in our lab level, So same thing, that is somewhat superior than available literature, so we are just testing whether they can be reproducible in commercial foundry so that it can be scaled out. And quantum key distribution chip, of course. And this is one of the success story, and because of our experience and long-term engagement in silicon photonics, we come close to Silterra. They have the 8-inch foundry for silicon photonics. Many startups, including IMEC and a lot of companies, they are using their process. However, they don't have their PDK, process design kit. And we had signed a MOU and started working on that. And first internal chip, their tape out happened recently. And we have already contributed in their tape out almost more than 100 different type of test structures which can be useful for quantum photonic circuit design and demonstration. So the following the things is that we will be designing and that will be fabricated in Silterra foundry. Wafer will come back to us, we will be testing, we will be giving compact model, and then ultimately we can come for the ultimate circuit design and probably packaging and field level testing. So that is our goal up to 2026. So with this, I should close my, so some of the packaging reports also we have started and working forward. With this, I thank you very much.
Thank you so much, sir, for your inputs. And now I would request for the next keynote address, Professor Kausik Majumdar. He's an associate professor in the Department of Electrical Communication Engineering at Indian Institute of Science, where he leads the Quantum Electronics Laboratory. His research group uses a combination of theoretical and experimental techniques, low-dimensional materials and their nanostructures, and applies these fascinating properties in developing novel devices for nanoelectronics, optoelectronics, and quantum technologies. Professor Kausik Majumdar.
All right. Trust me, I am as hungry as you. So I'll try to be quick. So, So as I just mentioned that, I lead the Quantum Electronics Laboratory at IISc Bangalore. So I'm primarily a device guy, so I love to develop components. And so a fraction of my lab actually works on some of these devices or components that are useful for quantum technologies. So one important thing that I believe is that which actually came out in the talks from many persons, that miniaturization is also important. Although we are in the initial phase of quantum technologies, but you eventually do have to miniaturize the devices, right? And because we love to make devices, challenging devices, so we already have working chips. So this is an example. This is a 5 millimeter by 5 millimeter chip, and all these different components, a single photon source, a single photon detector, a random number generator, all these working in the lab, indigenous technologies in a 5 millimeter by 5 millimeter chip. Of course, there is a small PCB associated with that, but the core IP is embedded in this chip. Okay. So particularly, the source, so this we use a principle called Coulomb blockade, and so it's pretty high rate. I mean, I think this data from the last week. So we have close to 10 megahertz, rate of single photons, with the G20 value of about 0.1. Okay, so it's quite high purity. We are of course trying to improve this. We have a single photon detector technology that is working at room temperature, and this is not a SPAD technology. This is again our own indigenous technology which uses some photo gating effect. We have an efficiency, of 21% for unpolarized light. If we used a polarized light, this is about 42%. This again, I think beats, in-gas pads, and this is, by the way, at 1550 nanometer. So, so that's interesting. So our goal is to, push it further, go at least, beyond 60% or so. So working at room temperature and 1550 nanometer, close to 60%, that will be, I think, a very interesting thing to have. Okay, so I was given the job of talking about random number generator today. So I'll probably so this is another chip that we have developed recently. I'll show you. We do this from a discrete electron fluctuation and try to measure the timing of that and get really high quality random number generation. All right. So just quickly telling you, so why we need random numbers. I don't want to go into details. This is already came up in many body's talks. Sorry. Hope it comes through. Yeah. So so you need, of course, increasing demand for hardware security, right? Do any digital transaction, whenever you see HTTPS in your browser, there is some security protocol that's going on in between, and there is a random number that's playing a role there, right? Of course, quantum communication, large-scale simulations, so which didn't come out very clearly. So like biology, chemistry, Monte Carlo simulations. Also, gaming, gambling. These are also good areas where random numbers are important. And how do you measure randomness? Purely from a random sequence point of view. Those who work in communication theory, they know is a Shannon entropy, which is commonly used. But Shannon entropy is something which tells you the average entropy or average information content in a sequence of bits, right? However, from a cryptography point of view, what we are more interested in is a mean entropy, which sort of what's the chance of predicting as a single guess? How easy for a hacker to guess, with single guess, right? So if you look at the equation, what happens is that if you have uniformly distributed symbols, that will actually maximize your mean entropy. And that's what we would like to look for. Can I have a sequence where the symbols are uniformly distributed? There is no preference of one symbol versus the other. That's the job. Okay. So some from a device point of view, that was from a sequence point of view. From a device point of view, the device which is generating the random sequence, so it should have a few good properties. So first of all, these different quantum mechanical processes, they are excellent sources of entropy. Okay, so like 2 + 2 4, this is a deterministic event. It does not have any entropy is 0. But if I tell you, sun rises in the west, there is a lot of, entropy in that, right? So here, what we would say is that, these quantum mechanical processes, like, a state, quantum mechanical, let's say you do some measurement, which state out of these different eigenstates, which eigenstate the system is going to collapse to. The system doesn't know. So this is a quantum mechanically random event, right? So this is just one example. There could be other ways of doing that also. But so there are other ways also to generate a random sequence. Like for example, there is a very complex process. You don't know all the details, so that would seem like random to you, right? Although there might be some hidden periodicity there. And this should be device independent. Then you should be able to prove that this is random. Because just proving randomness from a sequence is very difficult. You take 1 million sequence versus 1,000 sequence versus 1 giga sequence sequence length. There could be, so for example, if you're testing for a 1 million length sequence, there could be a hidden periodicity that is existing, let's say, at a 1 giga or something. You cannot see that. So it's sequence length dependent. So ideally, you should be able to prove that yes, this is a random sequence from the process itself, right? And of course, it should be unbiased. As I said, it should be like uniformly distributed. So although these quantum mechanical processes are excellent sources of entropy, however, having a nice compact, elegant readout, that is non-trivial. And that's why we come in as a device people, we can sort of try to do how to do the readout. So just quickly, so this is like, how it's done today through, some, noise, it could be a noise from an amplifier or from a, some electronic device, and you get, so this is not really true quantum mechanical, although, everything is quantum mechanics, but, there is an, sort of an averaging effect over here. It's not a, so-called, quantum random number generator. It is not. And people have seen, in the recent, past or repeated attacks on this, right? So what we do is that, as I said, we use discrete electron fluctuation and try to find out the timing information of that. So basically, if you have a Poisson arrival process, the arrival time is uniformly distributed. So that's the mathematics behind it. So we try to basically implement that in a electronic chip. So like I said, it's an all electronic approach, and that's why it can be very significantly miniaturized. It can in principle come in your cell phone. Okay, and so what we get, the mean entropy, which is 0.995, is the recent data. That's from an electronic chip point of view. This is the world record. So I would not go into details. We are all hungry, but there is a tunnel junction here. And in the tunnel junction, there is, which is an overlap area of about, let's say, a couple of 100 nanometer by a couple of 100 nanometer. And in that tunnel junction, there is a quantum well that is embedded. Okay, and an electron, can get trapped and retrapped into that, because, of the biasing of the device, things can get pulled into it or, go out of that, So the going out of that happens through a tunneling mechanism. And we have a, gate, top and bottom. What the gate does is that, it basically, turns off the region, outside this. And we make sure that the current actually flows through this tunnel junction, okay? So what really happens is that this is a discrete electron fluctuation probe. So what we do is that, the moment the electron comes in, because of Poisson's equation, what happens is that the voltage around that, or the potential around that region, it actually changes. And the moment the potential changes, it sort of acts like a local gate, and that changes the tunneling current through the device. So using a single electron trapping or getting retrapped, and by the way, the electron does not stay here forever because there is a high field, and through that it just gets retrapped quickly. Okay. So because of the single electron getting trapped or detrapped here, I have many holes which are tunneling through the device. So this tunneling current actually changes, and that is on the order of milliamps. I can measure that very easily. Okay. So whenever it gets trapped, I see a voltage output. It just comes down. When it gets retrapped, it again goes up. So the moment it gets trapped, that is the arrival time I would like to know. So that has to be nicely synchronized and all that. Through our post-processing electronics, we do it. And we basically digitize these points. And this is the digital output of that analog voltage. And you see, as I promised, sorry. So you see the the PDF, it's almost uniformly distributed. This we encoded into 8 bits, so this is 0 to 255. There are 8 bits. Is almost perfectly uniformly distributed. If you take let's say a certain length and count the number of zeros or number of ones, mathematically you can say that it should be a binomial distribution. And experimentally also we get almost perfect binomial distribution out of that. So it sort of gives you an idea that, and this is by the way tested over, I think, about 10 million bits or so. Okay? So that, it's a very good, random number by itself. Okay? So this is unbiased. And by the way, that was done at 7 Kelvin. It works at 295 Kelvin also. So it works at room temperature without any degradation in the entropy value. Okay, I can skip these more details. This is like, you can tune the entropy generation rate, by changing the biasing configuration. And we did all this, NIST tests. This 890B is a test for, whether the random sequence is truly random or not. It passes all these, and it gives us, the mean entropy number also, which is 0.983. That was a bit old data. The recent data is 0.995. It's almost near ideal. And it also, passes this 822, which sort of, tells us that it can be readily used for cryptographic applications without any post-processing. Okay. We also do our own statistical tests. Again, more details, but this K2 entropy should diverge if you have a really true and random number generator with a distance threshold. It does happen. And also, to check whether there are any hidden periodicity in higher dimensionality or all, this should be checked by this sort of test. So we saw that up to 8 dimensions, there is really no hidden periodicity in your sequence. On the other hand, if we take a Lorentzian or chaotic system, it actually saturates, you can see, at about 2, and that's what we expect. Okay. Fine. So yeah, so some benchmarking. As I said, this is a world record number in terms of mean entropy, particularly for those which is coming from the electronic domain. So yeah, that's all I have. So those who are interested, you can see this paper, for more details. And I would like to, thank my funding agencies and my students who actually do the job. Okay. Thank you.
Thank you, Professor Majumdar. Now we will be concluding the session with the last speaker of this session who has joined us online, Dr. Sadik Hafizovic. Do we have him here? He's virtually present with us from Zurich. He's the co-founder and CEO of Zurich Instruments. He co-founded the spin-off Zurich Instruments in 2008, and since then he has developed the company from an innovative lock-in manufacturer to a major T&M player and leading instrumentation provider for quantum computing. Dr. Sadik Hafizovic, can you hear us?
Yes, I hear you. Thank you very much for your introduction. I just need to find...
So you have about 10 minutes as you're the last speaker of this session, and after that we all break for lunch.
I will do my best. I just need to find my screen sharing. I seem to not be able to share my screen.
Sadik, this is Sushovan on the other side. You will be able to share your screen. In the bottom panel, you have a icon.
I'm sorry, I don't believe I have that icon.
Yeah, you can just write.
Now I have it. It just appeared. There we go. Awesome. Hey, yeah, I'm very happy and glad to be here. Thank you, the organizers, for inviting me. I have a topic that is a bit on the outside of the outside border of this conference on quantum communication. I'll be focusing on quantum computing, but of course, quantum computing, to be really taking over a serious role in the future, will also rely on quantum rings to actually have a scalable quantum computing system that includes more than
Sadik,
just one.
sorry to interrupt you. Your presentation is not visible.
The system says it does. I will try to share again, entire screen 2, share. Here we go. Is it sharing now?
Are you sharing the entire screen?
Yes.
Not visible till now.
Stop again, and I will start again. Entire screen 2. Screen is sharing.
Not visible. Can you just try to select a particular tab on the window? I will say the entire screen.
I was sharing the entire screen. I'm changing my setup now. Trying to Yeah.
Screen from the other camera, not from your I mean, the online participant can't see the video right now, PPT right now.
So if you could go to the next slide. So Zurich Instruments, we are a company starting.
Can you just upload the presentation? Can you just upload the presentation? You can see, I mean, you'll be able to see a plus symbol in the left bottom panel, I guess.
I don't think this will work. It will destroy the. Let's continue like this. It's a okay compromise to take. We're for 15 years. We started as a spin-off of ETH Zurich, which is also the place where I got my PhD. And today we're more than 150 people. We're very international, with more than 20 nations in the company. While we're based in Zurich, we also have offices in China, America, Germany, Korea, France, Japan, and then partners in countries like also in India. And since 2 years ago, we are part of Rohde & Schwarz, which in this context, next slide please, is very good news because Rohde & Schwarz is in India for already more than 25 years, and with locations in New Delhi, Bengaluru, Mumbai, Hyderabad. And this means that we can really, through our mother collaborate in Indian initiatives quite intimately. Next slide, please. Yeah, our quantum mission is very clear. We want to help build the quantum computer and be the leading quantum computing control system provider in the world. And next slide, please. We do this since about 2014, so quite early on, where single instruments were used to operate quantum computers. Since then, we have launched the world's first complete quantum computing control system, that's generation 1 in 2018. And by now, we have the second generation on the market, which is the Gen 2. And next slide, please. The Gen 2, it does away with all the external IQ mixers, no IQ mixing in the entire setup, so no more calibration of the signal processing system itself. It's just stable and it's purpose-built for quantum computing. Results in higher fidelities and accelerated execution. You can run more experiments per minute in your lab. And all that also needs a software framework, and we've recently launched our Lab 1Q, which is a Python-based user interface that is 100% targeted at quantum computing. Next slide, please. And the most recent addition is our SHF PPC. It's a parametric pump controller, which operates the quantum limited amplifiers that are in the fridge, the TUPAs. And this is an example of another piece of hardware that is 100% targeted at quantum. And together with the PPC and the generation 2 hardware and software, we provide the entire stack of room temperature electronics and software. Next one, please. So how does this help in the lab? Labs are very different. Here we have a spin qubit photo as an example for a few qubit setup. Here the important things are breakup and characterization performance, to be able to very dynamically and flexibly try out things. Those are usually smaller setups, but and flexibility matters here. Next slide, please. And the next step would be on the size of, say, 20 to 200 qubits. At that range, feedback becomes important for initialization, and it's also now possible to actually quantum error correction. Here I have a photograph, one from ETH stage where the world's first feasibility of the Surface 17 quantum error correction setup was demonstrated. You can see the setup. That's still a generation 1 setup. And on the right-hand side, there's the test bed from Berkeley, Lawrence National Laboratories, where also system sizes of around 40 qubits can be handled. And then finally, next slide please, we have the next generation coming up. This is going towards 1,000 qubits. And here the name of the game is to make tileable and distributed control. And here quantum communication comes in the sense that we need to network multiple different quantum processing units. And we've already done such an experiment on a smaller case at ETH. Also, HPC, high performance computing connectivity, becomes important here. We're working on this together with the Finnish company IQM. IQM is commercializing quantum computers, and we're providing the control system to them, and we're actually the link between the quantum world and the HPC. Next slide, please. For this, you need an architecture, our quantum computing control system architecture. It is a star architecture, which means from any point to any point you can come with one hop. It also means that we have one star per QPU, and if you now extend the system and you have multiple such PQSCs, that's the thing in the middle, you can network them. They can be spread in a local area network and operate multiple QPs at the same time. Going in the other direction, for one QPU can be structured into smaller parts. For example, what you see down here are ancilla qubits and data qubits. The ancilla qubits for quantum error correction. And next slide, please. You can see that for local feedback, we can read out some ancilla qubits, and if the ancilla qubits are high in the excited state, we want to reset them as fast as possible. And this can be done locally in the same instrument. So that goes very fast, less than 300 nanosecond feedback. However, to decode the error syndrome, we need to have global information and go through the center. Next slide, please. Which means that now the feedback path goes up to the PQC, where the syndrome is decoded, and then the data qubits are corrected accordingly. That feedback loop takes a bit longer, say up to a microsecond, and is dominated actually by the syndrome decoding time. So with this architecture, we're able to have a scalable system, one also that scales towards quantum error correction, but of course, next slide please, the most important part after all is the people. Next slide please. And the people are what really makes a difference. So at Zurich Instruments, we have more than 25 people that actually know how to operate quantum computers, that are able to bring them up. And with these people, we also collaborate a lot with our customers. It's a learning, it's a giving and taking relationship. We learn, but we also teach quite a bit because we do have some experience. Next slide, please. So as an example here, I have some collaboration projects. For example, the American Logic Cube. Here we built a quantum error corrected qubit, the first logical qubit. We do this in an international consortium with Professor Andreas Wallraff and Professor David Howell and others. In Switzerland, we also have another project with Andreas Wallraff. In Germany, the German Quantum Initiative. We're working both on the scaling and quality aspects. And in Europe, we, for example, have the Super QLAM, which is a local area network for quantum computers. Here we entangle two quantum computers that are more than 30 meters apart from each other. And that's kind of a milestone experiment towards scaling. We also bring the quantum computer to the internet, so quantum inspired in the Netherlands, for example, you can log on and enter circuits that are actually executed in our stack. Next one, please. We work also closely with startup companies. We are, so the IQM, for example, on the left-hand side, they are building those quantum computers in one of these boxes would be our control electronics. They have a roadmap for 150 qubits, which we worked out together, and HPC connectivity. So they buy our control electronics in order to focus on what makes a difference for them. And most recently, the American MIT spin-off Atlantic Quantum, they have also decided to work with us. And for them, the reduced capital requirement and speed up was the main decision factor. To be able to start based on what we've already done enables them to accelerate quite a bit in the bootstrapping phase. And what was also very important to those guys is that we are compatible to the global and international quantum software ecosystem. So there are other packages, like for example, Qiskit, of course, is the most famous one, that are very much compatible to our stack. Next slide, please. Now, I'd like, for the final part of my presentation, have a look at the real lab, at the real life. Big shout out to Andreas Varuguhes, who actually published a micrograph of the Surface 17 chip. So on the right-hand side, you can see the 17 qubits. There are ancilla qubits and data qubits. You can see the connections coming from the outside. And in reality, things are a bit messy. The schematic looks quite simple. In reality, you see that there are qubits. There's one in the center where lines are crossing other lines, and there's crosstalk, and we have to compensate for that crosstalk in our instruments. Also, the flux lines that tune the qubit have crosstalk to every other qubit, because the flux line, they inject the current, and the return current flows back through the ground plane, and the ground plane then induces a magnetic field in all other qubits. So we have a dense cross-coupling matrix. So for every flux pulse that we play on any qubit, we have to compensate on all other 16 qubits. That's a 17 by 17 matrix. So this is the reality of the lab, and we have to deal with it, and only by really getting and squeezing the lemon, we get the fidelities that were required on this chip. And with this chip, the world's first feasibility for surface code was demonstrated in nature. The next slide. Yeah, next please. Lab1Q, that's our software to program the system. Is really the key to rapid progress in the lab. And as an example here, I have a very basic measurement. Here we just frequency sweep a line. If we're looking for the qubits, there are 5 qubits in total. And when you look at the code, you see it's 1,000 points. And we have an integration time of 10 milliseconds. And that makes for a theoretical time to take that sweep of 10 seconds. Our system takes 10.5 seconds. That makes for a duty cycle of 95%. And this is really what is necessary for rapid progress in the lab. Next slide, please. Of course, also other measurements, more complicated ones, have to run at the theoretical speed limit. Here, for example, we do a qubit spectroscopy, but we don't do it qubit by qubit, we do it in parallel. So there's 5 qubits, the measurement happens in parallel. When you look at the code, there's a for loop on top. That for loop is not executed sequentially, but in parallel. And that's what Lab1Q does. And again, we run at 97% of the theoretical speed limit. Next slide, please. is that? That is the Ramsey slide. Yeah, Ramsey is another example, running really fast. In this case, it's a different type of looping. And well, lab 1Q, when you look at the code, I think the point I'd like to make here is you do not see on which instrument actually the channel is played. It just says use the signal drive, and somewhere else it's defined where drive is, which signal on what instrument. So you do not, you go away from the instrument level, you program the level above. And next one, please. The whole thing is also using a concept we call sections. It's a hierarchical way to structure your quantum circuits, and also permits to parameterize using those sections. They can be parameterized according to time, amplitude, phase parameters, but also to signals. So you could, for example, define a section for read out and apply to different lines. And the whole thing also, next slide please, really important, has debugging capabilities. So you compile the code, and then in the web browser you can see in the pull sheet viewer what the code is actually going to execute like. And this is on clock level precision, single clock cycle precision. So when you actually start executing the code, you know it's going to be what you have seen before. So the scope is not necessary anymore. You do the development, and it's our job to whatever shows, or to make sure that whatever shown in the pull sheet viewer actually comes out of the signal line. Good. And then on my final slide, what do we focus on today? Next one, please. Today, we continue our collaboration with research groups, and it's international. I hope India, with the quantum program that was announced now, is soon going to be on our list as well. And we are to substantiate this, we are also hiring in Asia. India would be really nice. There are open positions on our website. I'd like to advertise this to the audience here. And in general, we are further working on reducing the size, working towards 1,000 qubits, bringing down the price and complexity. And we will be launching more quantum big hardware products and a lot more automatization in software. Adding features, alarm compatibility, Qiskit Quasar is supported already today, Pipe we're also supporting, and speed up as the systems go larger becomes also more important, and quantum error correction is a very active research area that we're pursuing. Yeah, with this, I'd like to thank you for your attention, and I wish I could be with you today, and I'd like to thank you also again that I could participate in this.
Thank you, Dr. Sadik, for your presentation and for taking out time for us. Thank you. I request now Senior DDG TEC, Shri Rituranjan Mittarji, to present memento on behalf of TEC to the chair first, Dr. Suma Varuguhes. And I would now request Dr. Varuguhes to present mementos to all the panelists. Dr. Nixon Patel. Shri Nilesh Desai. Professor Bijoy Krishna Das. and Professor Kausik Majumdar. So if you can just step forward, we'll have a group photograph.